Hello, everybody, and welcome to another video in thermodynamics. This is Professor Algara, and we're going to keep covering information about chapter number 5. We were talking about mass and energy analysis of control volumes, and now we're going to start talking about engineering devices, how they behave, how we treat them as far as for thermodynamics analysis, and basically, we're going to learn the basics of them. Like I said in my previous video, this is one of the most important chapters because now we're heading towards um, entropy and the second law of thermodynamics. All right, let's get started.
So, a large number of engineering devices such as turbine compressors and nozzles operate for a long period of time under the same conditions once the transit startup period is completed and the steady operation is established, and they are classified as steady flow devices. So, what is the important part of this whole process? That the mass balance for a general steady flow system is given like this. The mass flow coming in is equal to the mass flow coming out. During a steady flow process, the total energy content of a control volume remains constant. Okay, these two things, number one and number two, are the most important thing when studying engineering devices. Okay, just remember that the mass flow rate coming in is equal to the mass flow rate coming out, and also the energy coming in is the same as energy coming out. And we're going to start by defining the different engineering devices that we deal with in thermodynamics. Okay, I'm gonna start giving you information about those devices. Whether heat is close to zero, work close to zero or not, delta PE, delta K, all that information that is given. So nozzles and diffusers are shaped so they cause large changes in fluid velocities and therefore kinetic energy. Okay, so nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hoses. A nozzle is a device, take a look at this. A nozzle is a device that increases the velocity of a fluid at expense of pressure. A diffuser is a device that increases the pressure of a fluid by slowing it down. The cross-sectional area of a nozzle decreases in the flow direction for subsonic flows and increases for supersonic flows. The reverse is true for diffusers. The energy balance for nozzles and diffusers is pretty much, energy that comes in, it's equal to the energy that comes out, okay, or the rate. All right, but the question would be, okay, how do I play with them and exactly how do I work with them? So nozzles and diffusers, they pretty much work in the opposite way. So when you're using, like I said, a nozzle, you will increase the velocity of a fluid at expense of the pressure, and the diffuser will do the opposite of that. Okay, but both of them will work under the same equations, under the same characteristics. They're just used for different applications. Whether you want to increase the velocity or not, or the pressure or not, then you will use nozzles or diffusers. So what do we know about nozzles and diffusers? So Q, it's pretty much close to zero. The workflow rate, it's also close to zero. My delta PE is also close to zero. So then if I keep using the equations, I have that the energy that comes in, it's equals to the energy that comes out. If you want to be a little bit more specific, I'm going to say that the theta 1 is equal to the theta 2. But if I multiply this by the mass flow rate, I can always do that. Okay, so I have a quick question for you. So which units am I going to get if I use those equations? Kilojoules per kilograms, kilograms per second, or kilowatts. So I'm just going to do a little bit of analysis before I keep moving on. So you know that theta, the units are joules per kilograms. Hopefully I'm not mistaken. The mass flow rate, it's kilograms per seconds. The theta, it's kilojoules per kilograms. They will cancel out and you will get kilojoules per second, which is equals to kilowatts. So the multiplication of this guy should be equals to kilowatts. And you can do that every time when working with engineering, with thermodynamics. But anyways, that was not important. I just wanted to tell you that. So I'm going to use the equation right here in order to develop the general equation for nozzles and diffusers. In nozzles and diffusers, the mass flow rate coming in, it's equals to the mass flow rate coming out. And I could call this just a regular mass flow rate. And if they are the same, I can cancel them out. And I'm just going to get that theta 1, it's equals to theta 2. Okay, if you remember what theta was equals to, let's just go back. Okay, so theta was equals to enthalpy plus, kinetic energy, potential energy. So I'm just gonna go back, start writing my equation. So enthalpy 1 plus kinetic energy 1 plus potential energy 1, it's equals to enthalpy 2, kinetic energy 2, and potential energy 2. Okay, what do we know? That the delta PE will be equals to 0, so these guys can cancel out, and at the end I'm only getting enthalpy and kinetic energy. So H1 plus V1 to the square divided by 2, it's equals to H2 plus V2 to the square divided by 2. And that's my general equation for nozzles and diffusers. Moving on, so now we get turbines and compressors. So pretty much they work in a similar way. Okay, they just do different things. For example, the compressor will require energy in order to work, and the turbine will generate energy. That's pretty much the two differences between them both. But if we keep a general equation, we could, as using the same thermodynamics sign, such as everything that comes in minus everything that comes out. In one case, the work will be required, in the other case the work would be given by the system. But anyways, a turbine drives the electric generator in a steam, gas, or hydroelectric power plants. As the fluid passes through the turbine, work is done against the blades, which are attached to the shaft. As a result, the shaft rotates and the turbine produces work. Compressors, as well as pumps and fans, are devices used to increase the pressure of a fluid. Work is supplied to these devices from an external source through a rotating shaft. A fan increases the pressure of a gas slightly and is mainly used to mobilize a gas. A compressor is capable of compressing the gas to very high pressures, and the pumps work very much like compressors, except that they handle liquids instead of gases. Well, like I said, compressors, compressors, fan, pumps, they work in a similar way of turbines, and it's very convenient that we analyze them together. So pretty much I'm just going to give information what they are. And one important thing, guys, as I'm adding information about the different engineering devices, it's really worth it that you write down everything I'm writing on the whiteboard right now, because that's what you need in order to work with these exercises. So when you have a turbine, you will have to remember what I'm telling you. When you have a nozzle or diffuser, then you will have to use the equations that we previously developed. All right, so moving on, we have the 4 turbines. Okay, so for turbines, we know that the rate of heat, it's pretty much or close to 0. The delta, guys, potential energy, yes, they do have But when I'm talking about the delta, is that the change, it's almost neglectable. Okay, so the delta of PE, it's close to 0. So now I'm going to use the same equation. The flow of the energy that comes in will be equal to the flow of energy that comes out. We also know that the mass flow rate 1, it's equal to the mass flow rate at the exit, and we're going to call that just a mass flow rate. In this case, I'm not going to cancel the mass flow rate because we have the power of the turbine involved into the equation. So if I want to keep adding or using or subtracting apples plus apples, then I need my mass flow rate in order to keep consistent with the units. So what would it be? I have the mass that comes in will be like this: mass flow rate that multiplies H1 plus V1 to the square divided by 2 plus GZ1, okay? And this is equals, this is everything that comes into the turbines. So what's coming out into the turbine? So let's call it the mass flow rate that multiplies H2 plus B2 to the square divided by 2 plus GZ2. What else? What else? I mean, that would be the question, right? The answer to that question would be that the turbine will produce work. Okay, so if the turbine is producing work, that means that the work, it's coming out of your system. So now I need to go plus the work, or the work rate that is coming out, the power that is coming out. So everything will be in kilowatts. So this whole thing will be kilowatts, kilowatts, kilowatts. Perfect. We can perfectly work with this equation. So this guy, as I said it's equals to 0 because there's no change in the potential energy. Okay, I mean, this guy is not equal to 0. Let me just put it better. PE1, it's equals to PE2. Therefore, delta PE, it's equals to 0. So I don't want to say that this guy, it's equals to 0. Just PE1 minus PE2 minus PE1 is just equals to 0 because they're identical. So if I keep just writing the equation, I will get the following one, finally. Mass flow rate that multiplies H1 plus B1 to the square divided by 2. It's equals to work out. Sorry. Okay. Work out plus mass flow rate that multiplies H2 plus V2 to the square divided by 2. Okay, so this is going to be for turbines, and now we're going with the compressors. So now that we've been developing the turbine equations, we're gonna move to compressors and fans and everything. Something very important about this equation. So like I said, this is the general equation for turbines. Sometimes, but just sometimes, okay, it's not all the time, delta KE could also be close to 0. When can I assume this, and when can't I assume this? So if you're given with velocities, okay, because the exercise was giving you velocities at the entrance and the outside of the turbine, then you will have to use a general equation. But let's say they don't give you any information about velocities. You could assume that the delta KE is close to 0. The change in kinetic energy is close to 0, and therefore the equation, this equation right here, will simplify even more. Okay, but those are just pretty much cases that could be given, and I just want to mention that to you. All right, so let's just delete everything right here. Perfect. So for compressors, okay, compressors, pumps, they will work in a similar manner. So now we know that delta PE is close to zero. Delta KE in this case is also considered close to zero. In this one, most of them, they're adiabatic, so the rate of heat is also close to zero. So if I use the same equation, the rate of energy that comes in, it's equals to the energy that comes out. And I'm going to use the same equation, and the same thing applies. So mass flow rate 1 is equals to the mass flow rate 2, it's equals to mass flow rate. Cool. All right, so now what I have, it's pretty much mass flow rate that multiplies H1 plus, let's say, KE1 plus PE1. What happened with the compressors? The compressors will require energy. Therefore, the work will be coming into your system. In the turbines was different. The turbines, the work was produced by the system. In compressors, pumps, all of them, they will require power. So now I need to add a work coming into my system. And this guy, it's equals to mass flow rate of H2 plus, let's call it KE2 plus PE2. Okay, what happened? So delta PE, delta KE, it's equals to 0, so I can cancel this with these two, and my equation will be simplified as work that comes in plus mass flow rate H1, it's equals to mass flow rate H2. And this equation will work for compressors, pumps, and fans. Alright, this is the equation I need when working with those engineering devices. This one, I actually don't know how to pronounce that, but it's the valve, finally, and we're going to develop the equation for that one as well. So the valves are even easier, one of the easiest engineering devices to work with. So pretty much they are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Okay, that's the most important thing. H2 is equals to H1. If I keep developing the equation, you know that enthalpy is equals to internal energy times or plus pressure times a specific volume. Same thing coming in or coming out. Okay. What do we know about the valve is that the rate of Q is equals to 0. They don't produce any work. Delta PE is close to 0. Delta KE, it's also close to 0. So if I keep solving the equation, I have that mass flow rate that multiplies H1 plus KE plus PE is equal to mass flow rate H2 plus KE plus PE. Alright, well, like you know, mass flow rate are the same. I can cancel them out. This will cancel with these two, and at the end I get that H1 it's close or equals to H2, and this guy is kilojoules per kilograms. Just remember that enthalpy is equals to internal energy plus PV. Let's just note how we've been using this equation since chapter number 2. It's just amazing. Okay, cool. Moving to the next engineering device, we have the mixing chambers, and I think that's the last one. So no, we have the mixing chambers, and also I think we have the heat exchangers. Okay, mixing chambers are very simple. In engineering applications, the section where the mixing process takes place is commonly referred as mixing chambers, which is here. This is where they mix. The mixing chamber does not have to be a distinct chamber. An ordinary T elbow, Y elbow in a shower, for example, serve as a mixing chamber for the cold and hot water stream. So pretty much a mixing chamber will be a device that will utilize to mix different fluids or to mix two different currents of fluids. Okay, the conservation of energy It's super simple. The conservation of energy analysis is simple to do. So what we need to know about this, it's that Q is close to zero. They don't produce work. It's also close to zero. My delta KE is close to zero. Delta PE is also close to zero. What else? Super simple. So energy that comes in should be equals to the energy that comes out. So if I have this equation, at the end, what I have is that the mass flow rate 1 H1. So this is 1, this is 2, and this is 3. So mass flow rate 1 H1 plus mass flow rate 2 H2 will be equals to mass flow rate 3 H3. Okay? It's simple as that. But if I keep developing, let me just write the equation again one more time. So we have something like this. And this is 1, this is 2, and this guy is 3. So pretty much what I had was energy that comes in. It's equal to the energy that comes out. Therefore, I get mass flow rate 1 H1 plus mass flow rate 2 H2. It's equals to mass flow rate 3 H3. And this is the general equation for mixing chambers. What is important about this, guys? Sometimes you're gonna have a mixing chamber with 2 entrances and 2 exits, or probably 3 entrances and 1 exit. That's when you need to be worried about, okay? Just use as a general equation that energy that comes in, it's equal to energy that comes out. And pretty much the mass multiplied the enthalpy will tell you exactly the energy that is going through this current, okay? All right, moving on to the next one and final device is heat exchangers. Okay, let me find my notes. Perfect. So heat exchangers are devices where 2 moving fluid streams exchange heat without mixing. Heat exchangers are widely used in various industries and they come in various designs. So this picture right here is one of the designs. So you have a hot fluid coming through this pipe, and then you have a cold fluid coming through the outside. So as you know, the heat transfer from one fluid to another, and those transmission of heat will be given by materials and different things. So pretty much we work in the industry with a lot of different things, a lot of different heat exchangers. In your car you have one. Is what keeps your car in a temperature that can work with no problems. You can also see it in there's so many applications for heat exchangers. That's what I'm trying to say. And you're gonna see that in multiple engineering systems, not only your car, but multiple. You have no idea how much you're gonna see it. So what happened with the heat exchangers? What do we know about them? They don't produce work. Okay, so this is equals to 0. Delta KE, it's close to 0 too. Delta PE is close to 0 as well. What else? They're usually adiabatic, but that will depend. Okay, this is close to 0 when the systems Okay, sorry, I was just typing. So Q will be equal to 0 when the system is taking as entire heat exchanger, sorry. When you take the whole heat exchanger, then Q will be equal to 0. How so? We'll take a look at this. So this guy right here is pretty much my heat exchanger. So you have water coming right here and water coming out right here. 25 Celsius, right here is 15 Celsius, 300 kPa. So you have the pipe that goes right here, and the pipe has refrigerant coming through here and refrigerant coming out with other properties. So what do we do with this? So my whole system will be the whole heat exchanger completed. And the only thing that I need to take into consideration would be, the things that crosses the boundaries. So if I take this as my system, the question you need to ask yourself, is the heat crossing those boundaries? The answer is no. And that's why heat is equal to 0. But let's say your system, it's gonna be the pipe. Oh, then that will be different, because we are transferring heat from and to the two fluids, right? And when that happens, the heat will cross these boundaries, and therefore you have to take into consideration the heat in your equation. But as a general equation, we always, most of the time, we take the system as a whole heat exchanger. So in that case, particularly, we don't need to worry about the heat coming in or out of the system, okay? So, well, like I said, let me just delete this guy. Perfect. All right, so moving with explanation. So, like I told you, there's no work interactions, there's no heat interactions, they're usually adiabatic. The whole heat exchanger, again, I'm repeating that, delta KE is close to 0, delta PE is close to 0. And now I'm just gonna use the equation, energy that comes in, it's equals minus energy that comes out, it's equals to the change, because it's a steady flow, this guy is 0, and I get that energy that comes in, it's equals to the energy that comes out. So we know, and we're gonna take this example, this picture. So 1, 2 are just water, and 3 and 4, they're just refrigerant. Everything that comes in minus everything that comes out will be equal to 0. So what's coming here? It's coming water. So mass flow rate of the water times enthalpy 1. That's coming in. What else is coming in? It's coming this guy right here, plus mass flow rate of the refrigerant times H3. It's equal to everything that comes out. So let's go with the water first. This guy, number 2. So that will be mass flow rate of the water, enthalpy 2, plus what else is coming out? This guy right here. So mass flow rate of the refrigerant, H4. And that's the equation. So again, I'm just gonna say the same thing as I said in the mixing chambers. Just start with this equation. Energy that comes in, it's equals to energy that comes out, or the rate of energy that comes in is equals to the energy that comes out. If you want to develop this equation a little bit more, you could also say that the mass flow rate of the water, it's equals to mass flow rate of the water multiplies H1 minus H2, and this is equals to the mass flow rate of the refrigerant that multiplies H4 minus H3. And I'm just simplifying more the equation. And the more information or more data you have, the easier it's gonna be for you. All right, so with that, we finished chapter number 5. I really like this chapter, guys. This is the baseline for chapter number 6 and 7, as we are getting more into systems and processes that involve more than one engineering device. For homework number 5, you're gonna see just exercises related with one engineering device particularly. But when we move into chapter number 6, then I'm gonna start explaining how to work with multiple devices. Let's say a pump, heat exchangers, a valve, things like that. So I want you to spend the whole chapter number 5 just focusing on learning how the engineering devices will work. Okay? What are the equations that I need in order to work with these devices? That's the key. If you learn that, then you will not have any problems for chapter number 6 and 7 and thermodynamics too. Because let me tell you something, this chapter is pretty much what we use in thermodynamics too. Okay, in thermo 1 we deal with 4 engineering devices, in thermodynamics 2 we deal with, I don't know, 8 devices or something like that. So one exam for thermo 2 would be probably 3 hours, close to that, or only one exercise. It's just, it is funny and hard. All right, guys, so that was chapter number 5. Again, go through the book. It's important that you read the book. It's not only what I'm explaining on the presentation, there is more information in the book. I will be posting my notes, the resume of the chapter that I always do for each one of the chapters. So now you have my presentation, you have the explanation of the presentation. I hope that's enough for you to understand or get an idea what these engineering devices are and how they work. Have an amazing rest of your day and go into your homework now. Thank you.